welcome to this afternoon's Oxford Discrete Maths and Probability seminar. It's a huge pleasure to have Matija Bucic with us from Princeton, and he's going to talk to us about Turran numbers of sunflowers. Matija, over to you.
So thank you all very much for coming, and big thanks to the organizers for this chance to speak. So as Christine already said, I'm going to talk about Turran numbers of sunflowers. And most of what I'm going to say is joint work with Domagoj Bradac, a very talented young PhD student at ETH, and Benny Sudakov. So let me, can I move this way? No. So, okay, so let me start by telling you what a sunflower is. So for me, a sunflower is just a collection of sets with a certain property. And the property is that if you take any two sets in the collection, their intersection should be the same as the intersection of all of the sets in the family. Okay, so let's look at some examples to make sure we're on the same page. So here is a collection of sets. All of them contain 1, 2, and are otherwise disjoint. So this is a sunflower because any two of them intersect in 1, 2, but also all of them intersect in 1, 2. So why is it called a sunflower? It's because it's useful to think about it in terms of these kind of pictures, where the sets consist of this central part and a petal, and then these 5 red kernel plus petal things are the actual sets of our sunflower. So we usually call this central part the kernel. So this is the common intersection of all of the sunflowers. It's denoted in brown here. And we think of the unique parts of the sets as petals. So they are here denoted in yellow. So this would be set 3, 4, 5, 6, 7, 8, and so on. So throughout this talk, I'm only going to talk about sunflowers consisting of sets of the same size. And by that, I'm going to say that they are uniform when I mean that all of the sets have size R. So for example, this is a 4 uniform sunflower. So sunflowers are some kind of basic fundamental objects, and they appear in various areas and settings. And in particular, they tend to be quite useful. And one of the main open problems, at least from the perspective of extremal combinatorics, is the classical Erdős and Rado sunflower problem, which asks for maximum size of a family of sets of size R, which don't contain a k-petal sunflower. So how many sets of size R can you place on a ground set of arbitrary size without creating one of these objects that we call a sunflower with k-petals? And this is about 60 years old. It's due to Erdős and Rado. It has many implications to other things. I'm going to mention a few in a moment. But for now, let me tell you what we know about the answer to this question. So a priori, it's not even clear that the answer is finite, because as I said, you can work with an arbitrarily large ground set. But it does turn out to be finite. And this is the content of the so-called Erdős-Rado sunflower lemma. They managed to show that you cannot have more than k to the r times, about k to the r times r factorial sets without creating one of these sunflowers. And yeah, so this is a very nice short argument. I've actually lectured it a couple of weeks ago. It takes about 15 minutes. And a bit later in the talk, I'm going to show you I'm going to use the argument behind this. So I'm not going to go more into this. But let me also tell you, like, the lower bound that Erdős and Rado gave when they gave this upper bound was similar to this, except it doesn't have this r factorial term. So it's about k to the r. And one of the big problems surrounding this question is whether this r factorial term is necessary or not. And there have been quite a few results which were improving this a little bit over the years. And then a couple of years ago, there was a major breakthrough due to Alvais, Lovet, Wu, and Chung, who managed to greatly improve this upper bound. And they originally got a bit weaker bound than what I stated here, but then there were a couple of papers optimizing their approach. So Rao got this dependency on R that I stated here. Then Terry Tao gave a different proof of this, which used Shannon's entropy argument. And then Bell, Hueluja, and Warnke got this dependency on K. So this is now the best upper bound that we know. And so if you want to compare the bounds, so what's changed here is r factorial is roughly r to the r. And here the base was replaced by log r instead of having r. And the actual conjecture is that this lower bound is closer to the truth and that we should be able to replace this log r with a constant. So this question is open even if you're working with these sunflowers which have 3 petals. And already this case is very interesting. So there is a non-trivial relation between this problem, which was observed by Alon, Špilka, and Umans, and the so-called fast matrix multiplication problem, which is one of the major open problems in computer science. And there are many other connections. And for example, this problem was a subject of a recent polymath project where researchers with various different backgrounds try to collaborate and make progress on this. So let me just mention one other interesting connection. So this was following this breakthrough result, Frankston, Khan, Narayanan, and Park used the ideas of this breakthrough paper and managed to prove an old conjecture of Talleyrand relating expectation thresholds and thresholds, which is also a very nice paper. But let me not go more into details about this, because today I want to talk about a slightly different but still closely related problem. So first, let me introduce a little bit of notation to help me talk about it. So I'm going to denote by SRTK a specific sunflower. So this will be the R uniform sunflower with K petals and kernel of size T. So, R uniform means sets have size R, K petals means there are K sets in this object, and size T, kernel of size T means the center has size T. So for example, this is, if you think of ellipses here as being sets and points as being elements of our ground set, then all of the sets here have size 2, so this is 2 uniform, kernel has size 1, and there are 5 petals, so this is S215. And in general, for this talk, it's going to be better to think of these sunflowers as hypergraphs. And a hypergraph is just a different name for a family of sets that comes with some additional useful notation. So for example, sets in a set family are called edges in the hypergraphs, and elements of the ground set are called vertices of a hypergraph. So with this idea, this S215 can be thought of as a 2 uniform hypergraph, meaning all sets have size 2, which just corresponds to a usual graph. And in particular, it is a star. So it's a star with 5 edges. So this is a reason why sometimes these sunflowers are also called generalized stars, since they give a very natural way of extending a definition of a star from usual graphs to higher uniformity hypergraphs. So another example is this, our friend from a couple of slides ago. So this was a 4 uniform sunflower. So 4 goes here, it has a kernel of size 2, 2 goes there, and it has 5 petals, so 5 goes there. And if we think of it as a hypergraph, it has the, like all of them, usually we draw hypergraphs if we can, using this kind of points, and ellipses represent edges or sets. So now, the Erdős-Rado sunflower problem can be stated in this language as asking for a maximum number of edges you can have in an R uniform hypergraph, which doesn't contain any of the R different types of, R different types of sunflowers of uniformity R with K petals. So these just vary according to how big the kernel size is. And coming from the perspective of extremal graph theory, it makes sense, maybe it's an even more natural question to ask, well, what happens if we forbid just a single one of these objects? This was asked by Duke and Erdős some 45 years ago, and they asked, so the question is, what is the maximum number of edges you can have in an n-vertex R uniform hypergraph, which doesn't have a fixed one of these sunflowers? And why is this more natural? Well, because it's an instance of perhaps the central problem of extremal graph theory, which is called Turran problem. And in that problem, we just replace this forbidden sunflower with an arbitrary forbidden hypergraph. And we're interested then how many edges can we put without creating this forbidden hypergraph. So this is why the answer to this question is called the Turran number. And it has been studied quite a lot. And in particular, we understand in the graph case, so when uniformity is 2, we understand quite well what the answer is. This is thanks to the theorem of Erdős, and Simonovic. But as soon as you move to 3 or more uniform hypergraphs, the answer to this Turran problem becomes much less well understood. And even for such basic families of graphs, such as these sunflowers, we don't really understand it that well. So I'm going to be denoting the answer to this question by exn of the forbidden sunflower, because this is also sometimes called the extremal number of this sunflower. This is where the ex comes from. So this is just to help a bit with the notation. So let me also mention that this problem itself captures several classical problems. And so, for example, if you plug in t equals 0, so that means we are forbidding a sunflower with kernel of size 0, which just corresponds to petals. And petals are disjoint, so we are forbidding k vertex disjoint edges. And in that case, this problem precisely corresponds to the famous Erdős matching conjecture, which is one of the big problems in extremal set theory. Another very interesting special case is if we plug in k equals 2, so then we are forbidding 2 sets which have an intersection of size t. So that means that we are looking for a family in which no 2 sets have an intersection of size t. And this is usually called forbidden intersection problem, usually attributed to Frankl and Wilson, since their algebraic arguments first solved it. And this specific problem has found applications to quite differing areas, such as discrete geometry, computation complexity, and even quantum computing. So there are some very interesting special cases, and people looked at various regimes of this problem, and there are various results. But today I would like to talk about this problem in kind of full generality in some sense. And in this direction, there is a nice result of Frankl and Furedi from 1995, which determines if we fix the uniformity and the size of the sunflower, it determines this Turran number up to constant factors. So this gives us some kind of understanding of this Turran function, but natural next question is, well, can we get a bit better understanding? Can we maybe determine the correct dependency on R or on K? And this question, at least in terms of correct dependency on K, was raised in several places by Chung, Erdős and Graham over the 1980s. And they asked it with a certain specific application in mind to a so-called unavoidability problem, which I'll tell you maybe a little bit about towards the end of the talk. But it's a very natural question on its own. We're just trying to understand this function better. So we want to have a similar result just with the correct dependency on n and k. So let me tell you what we do know. So in the 2 uniform case, this is fairly trivial because forbidding, there is only one interesting sunflower, which corresponds to forbidding this star with k edges. So this is equivalent to asking how many edges you can have in a graph which has maximum degree less than k. And the answer to this is just roughly nk, and it's fairly trivial to even determine it precisely. But note that this is an observation which is actually used quite a lot, and we just use it without thinking. Whenever you have a graph which has maximum degree k, we just say automatically it has at most nk edges. And we often use this with k growing with n. So we want to be able to plug in root n here, and this is often very useful. So in some sense, this question is asking, well, can we get a similar kind of result for more uniformities, for higher uniformities? And forbidding this sunflower can be thought of as some kind of codegree-like restriction on your hypergraph, which is fairly natural and occurs in several instances. So the free uniform case is also relatively well understood. So here, there are two different types of interesting sunflowers. So I'm ignoring the third one, which would have the zero-sized kernel, since that corresponds to matching, mostly because that's fairly easy to solve if we only want approximate results. And it's kind of behaving a bit differently because it doesn't, in some sense, correspond to this generalized star idea that I keep in mind about this sunflower. So the one on the right turns out to be a bit easier. It has two things in the kernel, and the answer here is just n squared k. And the upper bound is fairly easy here. It just follows, since if you take a hypergraph with n squared k edges, in total you have n choose two different pairs of vertices. So just by a basic pigeonhole argument, one of these n choose two pairs needs to be in at least k edges. And the pair of vertices belonging to k edges of size 3 precisely means that you find this sunflower. So the lower bound is the more interesting part for this one, and it comes from taking an object which is called the Steiner triple system. So this is just a free uniform hypergraph with the property that any pair of vertices belongs to exactly one edge of this hypergraph. And it will have, then it's easy to check that it will have about n squared edges. And so this will give us a lower bound of n squared. And since every pair is in a single edge, then it doesn't have this sunflower. But we want to get another factor of k. And the way you can do this is you take k minus 1 copies of this Steiner triple system. You just randomly permute each one. So we permute them randomly because that will ensure that kind of you don't get collisions between these different things. Because if you take multiple Steiner triple systems, maybe some edges appear in both, and then you don't really get new edges. But each Steiner system has about n squared edges out of the n cubed in total. So it stands, and it's not hard to check that actually there will be very few collisions, and you will get about a small constant times n squared times k minus 1 edges from this union of k minus 1 Steiner triple systems. And still this picture will never have this sunflower, because if you look at any pair, it belongs to at most one edge per Steiner triple system, and we put k minus 1 of them, so you can never find k edges which contain the same pair. And if you do this a little bit more carefully, you can determine the answer here up to lower order terms. And as far as I'm aware, no one actually wrote down what the answer should be precisely. And a bit of an issue here is that Steiner triple systems have certain divisibility constraints. So yeah, but it might be actually an interesting, perhaps easy problem to figure out this one precisely. So the other one is a bit more interesting in terms of the upper bounds. So this is far less trivial than the other one. And the answer here is nk squared, which you should think of it as being a bit smaller than this one, because while k is allowed to grow with n, if k becomes linear in n, then the answer becomes trivial. So for example, if you are asking really for k equals to n, then you just cannot fit this sunflower on n vertices. So the question is just, the answer is just complete hypergraph, nothing interesting going on. So you should always think of this parameter k as being smaller than n, but allowed to grow with n. So something like root n is maybe a good thing to keep in mind throughout the talk. So here in this answer, we replaced one factor of n with a factor of k, so it's smaller. And in some sense, this is the reason why this upper bound here is harder and lower bound is trivial. So this one was solved by Duke and Erdős in their original paper up to constant factor. Then Frankl got the slightly better bounds. And following that, there was a paper of Chung, a very nice paper, which used some weight shifting arguments to actually determine the answer in this left case up to lower order terms. And then following that, another very nice paper of Chung and Frankl managed to determine this Turran number really precisely. So the free uniform case is reasonably well understood, but the situation stood here for quite some time. And only a couple of years back, together with Draganic, Sudakov, and Tran, we managed to solve the 4 uniform case up to constant factor. And then we use this to solve this unavoidability problem that I mentioned before in dimension 4. So yeah, and the result that I want to talk about today is what happens in more uniformity. So we managed to get a similar result for any uniformity. So the main result that I want to talk about today is determination of this Turran number of a sunflower, which is correct, which has the correct dependency on both n, which is the size of the ground set, and this k, which is the size of the sunflower itself. And I understand this is a bit kind of notation heavy and messy statement. So let me rather try to illustrate what the answer is on an example, and then say what happens based on this example, what this theorem is actually saying. So let's look at the 5 uniform case. So this was the first open one. And here I'm including this sunflower with empty kernel just to preserve symmetry, and because it does obey the statement of the theorem. If you plug in t equals 0, you'll get the correct statement. So the answer here is n to the 4 times k, and this is really very easy. The next one is if we have 1 vertex in the kernel, and here the answer is n cubed k squared. So we removed 1 factor of n and replaced it with a factor of k. So this is a bit smaller. It's correspondingly also a bit more difficult. So this is about as difficult as the S3 1k from the previous slide. So it requires a bit of work, but it's doable. So by far the most difficult case in the 5 uniform case, which took us some time to figure out how to do, is when we have 2 vertices in the kernel. So here we once again replaced another factor of n with a factor of k, so the Turran number is even smaller. And this is in some sense the turning case. So what happens here is that the kernel becomes of the size approximately the same as the petal. So at this point, the behavior will flip. So we will change from one of the regimes to the other. And now instead of Turran number decreasing, it's going to grow as you add more vertices to the kernel. So the Turran number of this sunflower with 3 vertices in the kernel is now n cubed k squared. So we replaced 1 k factor with an n factor. And this now again keeps happening as you keep adding vertices, that it keeps increasing, and we keep replacing a factor of n with a factor of k with a factor of n. So overall, the same thing happens in general uniformity. You start at n to the r minus 1 times k, and then as you keep adding vertices to the kernel, you keep replacing a factor of n with a factor of k, all the way until you hit this so-called balance case, in which the size of the kernel is about the same as the size of the petal. So this would be the case when both regimes are actually true. And at that point, the answer starts to grow. So now we replace factors of k with factors of n until we get back to n to the r minus 1 times k. So this theorem is saying that this actually happens for any uniformity, and that the answer is this kind of symmetric convex function as you increase the number of vertices inside of the kernel. Very good. So are there any questions? I see something in the chat. Okay, sorry. I was not looking at the chat, so I would appreciate if you would unmute yourself or however this works. Very good. So I would like to tell you a little bit about how we prove this result. And I'm going to focus mostly on the upper bounds, since they turn out to be quite a bit more interesting. The lower bounds are also fairly nice. They use these Steiner systems, so I gave you a little bit of a taste on this free uniform case, and they do require a bit of modifications to this in order to get them to work for any k, because k can grow with n. That's the really important thing here. But the upper bounds somehow have some very surprising connections to other fields and problems. So I want to focus on them. So let me begin by telling you an overview of how we prove this result. So first, we use induction to reduce this general problem, so bounding all the various different sunflowers, to just the single case of bounding this balanced sunflower. So for me, a balanced sunflower is just this sunflower in which the kernel has size t and petals have size t plus 1. So as I said before, this is the one in which both regimes agree. This is the one which has the smallest Turran number. So it stands to reason that it should be the most difficult case. And in this step, we formally kind of prove that this is indeed the case, so that you can reduce all the other cases to just proving this upper bound. And I want to point out that even this is not so trivial, because note that this balanced sunflower is always of odd uniformity. So in particular, if we know this step immediately covers the 4 uniform case from our previous paper, since the 3 uniform case was known for about 30 years before our paper. So there is a little bit of work involved here. But in some sense, what happens here is that we push the methods from our previous paper to the limit, and this allows us to get this reduction, but it's completely, we need completely different things to deal with this kind of the most difficult case. So very good. So now we want to just prove this inequality. And the second step is a reduction of this inequality to an existence problem for an object which is called t plus 1 t system in literature, and which I will now tell you what it is. So it's just a family of sets which satisfies certain properties. And the properties might seem a little bit arbitrary, but they somehow appear relatively natural when you have a certain argument in mind here. So the properties that I wanted to satisfy are as follows. So I want it to be intersection closed, which means that if you take any 2 sets in the family, their intersection should also be in the family. If you take any subset of size t of the ground set, it should be contained in some member of our family. And the third one is that for every member of our family, its size should not be congruent to the size of the ground set modulo t plus 1. So as I said, these conditions might seem a little bit arbitrary and coming out of the blue. So it's quite remarkable that kind of this bound really reduces to whether such an object exists or not. But what is even more remarkable is that this same somewhat strange object appears in completely unrelated problems. So for example, in a paper of Nagel, Sudakov, and Zenklusen, in which they were looking at a certain submodular optimization problem, so nothing to do with sunflowers or extremal graph theory, they also reduced their problem to the existence of such objects. And in the process, they also proved that they do not exist whenever t plus 1 is a prime power. So using their result together with our reduction proves this inequality whenever t plus 1 is a prime power. And so natural next question was, well, do these objects exist when t plus 1 is not a prime power? And they asked this, and quite remarkably, yet another paper coming from a third direction. So Brakenship, Gori, and Guruswamy were studying a certain constraint satisfaction problem in theoretical computer science. And they also reduce a certain problem to existence of these t plus 1 t systems. And they show that, unfortunately, these objects do exist whenever t plus 1 is not the prime power. So we were quite stuck at this point for a while, because our argument kind of really reduces this to whether such a t plus 1 t system exists or not. But luckily, what comes to our rescue is that the t plus 1 t systems that arise in our proof will always be on a relatively small ground set. So what we actually want is that such an object does not exist with capital N being equal to 2t plus 1. And these examples of t plus 1 t systems, when t plus 1 is not a prime power, require very massive ground sets. So what we managed to prove is that actually, indeed, these objects do not exist, provided the ground set is small. So in particular, if the size is 2t plus 1. And then this result, together with the reduction, proves this in full generality. And then this step induction from the first step proves our theorem for any forbidden sunflower. So that's the overview of how the proof works. So I'm not going to discuss the first step because it's somehow ideas that already existed. So pushed a little bit, there is some new things here as well, but it's a little bit technical and perhaps hard to follow. But so I'm going to focus more on step 2 and 3. And in the second step, I want to at least give you some kind of intuition how these strange t plus 1 t systems appear in relation to this problem. So again, I'm not going to really be able to tell you the full proof of this step, but I hope I'll at least be able to give you some intuition about it. And then I want to show you I'm not going to show you step 3 either. I'm going to show you a different proof of the fact that this t plus 1, that when t plus 1 is a prime power, these objects don't exist, because we have a much shorter proof which uses number theory instead of algebraic methods, which were used by Nageles, Sudakov, and Zenklusen. And this is a fairly short and nice argument. So I thought it would be a nice thing to close this down. And this full step 3 uses a very nice result of Katona and Frankl and Katona, which but it again takes a little bit of wrapping your heads around what's happening with the sets. So I thought that for the end, it might be nicer to just do a number theoretic nice argument, which kind of implies the results that these two papers want. So let me begin with this step 2. And what are we trying to do? We're trying to show that if you look at if we assume that there is no such object as this t plus 1 t system on 2 t plus 1 points, then we have this upper bound on our forbidden balanced sunflower problem. And the upper bound is a big constant times n to the t times k to the t plus 1. So let's see what's the setting of this problem and what we need to do. So we start with hypergraph H, which has n vertices. It's 2t plus 1 uniform. It does not contain a balanced sunflower. And we're trying to show that it has at most this many edges. And in the process, we are going to use the fact that these objects do not exist. Okay. So first, let me show you how we are going to use the fact that our hypergraph is balanced sunflower free. And we're going to do that as follows. So we look at any set S of t vertices. And I claim that because there is no balanced sunflower, we can find a small set of vertices tau S, which we think of as a certain cover set, which is disjoint from S and which intersects all edges which contain S. Okay, and by small, I mean it should have size at most t plus 1 times k. And here, remember, t plus 1 is smaller than uniformity, so this is a constant for us. So the size of this is actually roughly k. So let's look at the picture. So here is our t element set. And let me show you why such a small cover set exists and what this object actually is. So we look at our t vertex set S, and we look at all the t plus 1 sets which extend S into an edge of H. So the hypergraph consisting of these t plus 1 sets is called the link hypergraph of S. And what we want to say is we want to find a so-called cover of this link hypergraph. So this tau of S, which will intersect every edge of this link hypergraph. Okay, this is a fairly easy thing. So the reason is that we can't have k vertex disjoint edges in this link hypergraph, because if we did, then they could make petals, and together with S being a kernel, this would give rise to this balanced sunflower. Because each of these guys extends S into an edge. So if you look at this as being a kernel, if they are vertex disjoint and there's K of them, this precisely corresponds to a balanced sunflower. So now, okay, so we cannot have more than K such vertex disjoint objects. So we just take a maximal collection. And I claim that if you take the union of the vertices of this maximal collection, this will give us a cover. And the reason is, so the size constraint is easy. We have less than K of them. Each of them has size T plus 1. So their union will have size at most T plus 1 times K. And it covers every T plus 1 edge in the link hypergraph. Because if there was one which is disjoint from all of these T plus 1 sets, then you could use it to extend our maximal collection, right? If it's disjoint from everyone, we can just add it to the collection. So that's a contradiction. So really everyone needs to intersect their union, and this tau S is indeed the cover. Very good. So this is fairly standard hypergraph stuff. So let me now clean up the slide a little bit. So as I said, this is the only way in which we are going to use this balanced sunflower free condition. And in particular, we are going to, so I'm stressing here that we are fixing such a cover. So there might be multiple covers which work, but I want to fix them for every subset S of T vertices. And from now on, this is going to be the cover of S. Of, well, link hypergraph of S. So now let's see an kind of an easy observation and try to show some kind of upper bounds on the number of edges of H. So I'm going to be denoting by E of X the number of edges which contain set X. So this is just the size of the link hypergraph of X, if you prefer it that way. And a trivial observation is that the number of edges in H is at most the sum of the number of edges that contain every T element subset. So we go through every T element subset, we see how many edges contain it, we add up all these numbers, and we've counted every edge at least once. We've actually counted every edge many, many times, because the edges have size 2T plus 1. They each contain 2T plus 1 choose T sets of size T. So in total, this is how many times they get counted. But remember, 2T plus 1 choose T is just a constant for us. This is possibly not such a bad thing, but it will actually be important that kind of in this sum, each edge is counted multiple times so that we can modify these ESs to not count all of the edges which contain S, but in some sense we choose for every edge for which S it's going to be counted. But for now, this is just a trivial inequality, and it doesn't really give us anything on its own, but with an extra step, it will give us a slight improvement over the trivial bound that we can get here. And the trivial bound is just n to the 2t plus 1, because this is how many edges you can have in a 2t plus 1 uniform hypergraph. This is how many sets of size 2t plus 1 there are. And the step that lets us save a little bit is going to use the existence of these small covers of link hypergraphs. So in particular, if we have our T set S, and we're trying to bound how many edges contain it, so we're bounding the size of a link hypergraph, then we know that every edge in the link hypergraph is covered by this tau of S. So if we count the number of edges which contain S together with each of the vertices in our cover, then we still count all of the edges that contain S. So in particular, there are at most T plus 1 times K such vertices V. So we get in this inequality, so we get T plus 1 times K summons, and each of the summons is at most n to the T, because it's counting T element subsets. So there are at most n to the T of them. So putting together that here we had n to the t different sets of n choose t, but n to the t is the same if we don't care about constants for me. So we have n to the t different summands here. We have t plus 1 times k here, and each of them is at most n to the t. So what we get is n to the 2t times t plus 1 times k, which you can think of as just being n to the 2t times k, because this is a constant. So we managed to improve n to the 2t plus 1 to n to the 2t times k. So we replaced one factor of n with a factor of k. We made a slight improvement over the trivial bound. But in order to get to this desired bound, we need to do this many more times. And so how do we do that? So first, the obvious choice would be to try to do this now with this fixed t plus 1 vertex set. So try to say that its link hypergraph has a small cover. But we only have this property for t element sets. And if we knew that not only we don't have a balanced sunflower, but that we also don't have the one with kernel of size t plus 1, then we could just trivially repeat the same thing. So we could find a small cover for t plus 1 element sets, and this would guarantee us a small cover here. But unfortunately, we can't do that if we're just forbidding this balanced sunflower. But what we can do is say, imagine that we managed to find a t element subset of this t plus 1 set, so denoted here with the red vertices, with the property that the cover of this red t element set does not contain the blue vertex. So it does not intersect our set of t plus 1 vertices. Well, in that case, this is also a cover of the link hypergraph of this t plus 1 element set. Why? Well, because it covers all of the edges which contain just the red vertices. So in particular, it will also cover the ones which contain also the blue one. And since the blue one is not in the cover, all of these cover vertices need to be new vertices. So what this means is that we can do this once again. So we can again go through all of the choices of t plus 1 times k vertices, which live in the cover of this red t element set. And this will reduce the problem of counting how many edges contain this t plus 1 element set to the problem of counting to k, at most t plus 1 times k smaller problems, of which count how many edges contain these two t plus 2 element sets, obtained by adding each of these vertices of the cover to the t plus 1 element set. And in general, if at the moment we're trying to count how many edges contain a set X, if we can find a t element subset S of X with the property that its fixed cover does not intersect X, then this is a cover of its link hypergraph, and we can do our argument and just reduce and kind of divide and conquer and split into t plus 1 times k smaller subproblems. So unfortunately, this is not always going to happen. So there might be some sets X in which we get stuck, in the sense there is no t element subset which allows us to repeat this argument. But what we'll do in that case is we're just going to say, okay, tough luck. We're out of luck for this summand, say X union V, which did not have a proper t element subset which allows us to continue. And we're just not going to count the edges that contain this stuck subset X. Okay, so we're just going through this counting branching process, and some branches we end up in a stuck set, and we say, okay, tough luck, we don't do anything, we don't count edges which contain that set. So the problem now is that maybe we don't no longer count all of the edges, because, well, when we are stuck, we just give up on some of the edges. But what comes to the rescue is this fact that every edge lives in many different, contains many different subsets of size t. So if we run this argument starting from any t element subset, as we do, this is this first step, then so long as we count that edge for some t element subset S, we are happy. It can be stuck in every other t element subset S, and we're still good with that. And so in the case, really every edge was counted at least once through this process, then we really get our desired bound. Because in every step, we are branching in at most this many steps. Maybe some branches die down, but that's only helping us in some sense. And in total, we do this t+1 many times. So we have n choose t choices for the first t element sets, t+1 times k for every of the remaining t+1 vertices through this kind of, this is how many branches you get. So in total, we get n to the t times k to the t+1 many edges. And I'm again ignoring these t+1 constant terms. So very good. So this would work. The only problem is if there is an edge E which didn't get counted for any of its t element subsets. And in that case, I claim that this edge E is going to induce this t+1 t system on its vertices. So note that this is where the 2t+1 comes in from. This is just the size of the edge, which we didn't count in this process. And for example, just to illustrate where the other properties come from of the, so also, what are the sets going to be? So the sets that make the t+1 t system are going to be all the stuck subsets of this edge. So any x in which our procedure got stuck while trying to count E, our uncounted edge, is going to be a member of our t+1 t system. And observe that this guarantees that, for example, it covers all t element subsets, simply because we start this argument from every t element subset, and we're assuming we never counted E. So in this branching procedure, at some point we got stuck at the set X, which is a subset of our edge E. So in particular, it contained this arbitrary t element subset. So all t element subsets need to be covered by these stuck sets X. And it's also easy to see that the size of X is not going to be equal to T at any point, because we don't get stuck at set of size T just by how we define this cover, right? It's disjoint from the T element set. So the first step we can always do. And this will correspond to the third requirement of our t+1 t system. So the only issue is the intersection clause property. And if you really try to do what I told you here, it might not necessarily be satisfied. There are certain degeneracy problems that pop up. And what we actually do is we need to do some kind of a little bit more involved argument with a bit more acrobatics, which I'm not going to tell you how it exactly works. But this is really at the heart of the proof. And this happens in the background. It just gets a little bit more notation heavy when you want to kind of avoid this degeneracy. So I hope this gives a little bit of intuition how these systems appear. So somehow either this branching procedure succeeds in counting all the edges of H, and then we know that the number of edges is at most the desired one, or we end up with an edge which is not counted, and then it induces this kind of t+1 t system from the previous slide. So very good. This is all I wanted to say about this second step. So let me tell you a little bit about the final step. So the step 3, in which we show that such objects never exist. So that kind of our previous argument always works. So as I said, I'm only going to do it for prime powers. So when t+1 is a prime power. And let me remind you also what are the properties of a t+1 t system. And I'm assuming here towards contradiction that they all actually exist. So I'm assuming that A is intersection closed, that all the T subsets of the ground set are covered by members of our set family, our system. And also I'm assuming that the size of our system is not congruent to the size of the ground set modulo T+1. So these were the 3 defining properties of t+1 T system. So the first step is relatively easy kind of technical thing to help us with number theory that we want to do. So we are going to add a fixed set of dummy vertices to every member of our family. and these will be new vertices. So they also increase the size of the ground set and the size of every set in our family. So in total, this condition is going to be preserved because both these terms increase by the same amount. It's also not hard to check that by doing this, also the other things get preserved. But this allows us to kind of choose, in some sense, how big our ground set is going to be, and in particular, choose it to be congruent to -1 modulo t plus 1. So note that in our actual application, the capital N is going to be 2t plus 1, so we just get this step for free. But I wanted to include this step to also include the more general version that was needed for the other two papers. So now let me denote by A1 up to AM the sets in our family. And let's double count the number of T sets, T subsets of our ground set, which are covered by some member of AI. So on one hand, this is trivial because we are assuming that all of them are covered by someone. So in total, this is always equal to capital N choose T. But we can also count it in another way. We can go through our members of our family and use inclusion exclusion. So how many sets are covered by the first set? So this is just the size of the first set choose T. This is how many sets are covered by the second member of our family, how many T subsets are covered by the last one. And here we overcounted any T subset which is contained in multiple members of our family. So we get here, so we need to take out the A1 intersection A2 choose T and so on. And now we're undercounting, so we need to add the triple intersection choose T and so on. So in total, just the basic inclusion exclusion principle gives us this expression as also being equal to the number of covered T subsets. So let me write it in a bit more compact way. So this is exactly the same as the inclusion exclusion I've written down there. And let me point out what is, you really don't need to worry about the sum. The only interesting thing here are going to be these binomial coefficients. And in particular, the fact that all of them have in the top part the intersection of some members of our family. So in particular, by the first property, this is also a member of our family. So it needs to satisfy the third condition. In particular, this number is not congruent to capital N, so not congruent to -1 modulo T plus 1, which is this prime power P to the alpha. And now a basic result from number theory called Lucas theorem, which allows you to compute the residue of binomial coefficients modulo prime, immediately tells you that this means that each of these binomial coefficients is divisible by P. So since each of them are divisible by P, that means the whole sum is divisible by P. And on the other hand, it also tells you that this binomial coefficient, where N is congruent to -1 modulo P to the alpha, is not divisible by P. So, and that gives us our contradiction. So this side is not divisible by P, this side is, they should be equal, so such objects cannot exist, and we're done. So this, I'm not going to tell you how Lucas theorem is proved. It's a result from late 70s, but it's a very useful thing to keep in mind if at any point you want to kind of figure out some binomial coefficient modulo prime. And also it breaks badly if you try to do it modulo something which is not a prime. So, and also, as I said, there are examples of such objects which there are examples of such objects when T plus 1 is not a prime power. So this argument really can't work in general. And we need to do something else, which is also nice, but would take me a bit more to present in that case. So this is all that I wanted to say about the proof. So let me quickly wrap up. So we managed to determine the correct dependency of this Turran number of a sunflower on both the size of the ground set and the size of the sunflower we are forbidding. And the natural next question is, well, what can we say about the dependency of this on R, the uniformity? So this is the remaining parameter which we kind of want to understand. So if you want to give an explicit answer to this, I think that would be very hard. and at the very least include the proof of the Erdős-Rado sunflower conjecture, because somehow the same issues pop up, and there is even a conjecture of Frankl and Furedi that the answer to this question is controlled by the answer to the Frankl and Furedi for half of the regime, of Erdős and Rado. So and they prove that this is indeed the case for a decent chunk of this half of the regime, but they only do that when K is constant. But some kind of this less implicit result might also be interesting, or improving R dependency on R also might be interesting. So the second question I want to mention is kind of simultaneous generalization of both the single forbidden sunflower problem and the Erdős-Rado sunflower conjecture, where we forbid all of them. So what if we forbid some subset of all the types of sunflowers? So this we solved up to dimension 7 or something like that, because we were trying to use it to prove our single forbidden sunflower problem. So to give us a stronger induction assumption in some sense. And I still don't know, even the correct dependency on N and K, it wasn't quite clear from this up to 7. So it's possible that this might have some very interesting behavior. And I think our ideas that we developed after that could be very useful to solve this problem. And finally, just briefly, this let me mention this unavoidability problem that I mentioned before. So it's due to Chung and Erdős from 1980s. And it asks, loosely speaking, among R uniform hypergraphs with a fixed number of edges, which one is hardest to avoid? Or a bit more formally, if you want, which one has the minimum Turran number? And this was solved for 2 and 3 uniform case up to constant factor by Chung and Erdős. And we solved it in this paper a couple of years ago in the 4 uniform case. And this understanding these sunflowers is kind of a first step you really need to understand in order to solve this problem. So now this step is done, and this is somehow also maybe a bit more approachable than before. There are some other issues here, but it's a very interesting problem. And now we've made the first step towards something. So let me stop here and thank you for your attention.
Thank you, Matija, for a lovely talk. Can I ask, has anybody got any questions? So I think Alex has a question. Alex, go ahead.
Thanks for a very nice talk. Is there a natural conjecture for problem 3, for the last one?
So it's a little, so the reason why these sunflowers are important here is because there is some kind of conjecture. It's a little bit complicated. There are multiple regimes of which graphs are optimal depending on how many edges you're working with and what's the relation to what's the ground set for the Turran number. But they're always, except at the very end of the regime when the problem is a bit easier, they're always based on these sunflowers. So somehow you need to generalize them a little bit. So somehow the thing that's missing here is understanding this even more generalized version of a star, let's say, of a sunflower, and understanding the Turran number of that. But somehow it contains a lot of these specific sunflowers inside. So if you don't understand how many edges you need to avoid that, there is kind of no hope in solving this problem, at least based on this up to 4. So by that, I mean, now we understand, I think, reasonably well what the answer should be in general. But it would take me a while to actually give you explicitly in what regimes the answers are. They're never just these sunflowers, but they're very similar to them. Kind of, you multiply some vertices and so on.
If you assume the sunflower conjecture, does it help at all?
So if you assume the sunflower conjecture for this, not really. They are kind of a different problem. So somehow in the sunflower conjecture, the dependency on K is fairly trivial. We know that it's K to the R. And if you treat uniformity as constant, in this problem, really, sunflower, at least if you care about N and K, is easy. The Erdős-Rado sunflower problem. But yeah, it's not, so in some sense, they are different directions. And only if you try to merge the 2 directions, then you kind of get a bit of a different perspective on 2 problems. And this would be very interesting, I think. I mean, specifically because going towards the sunflower conjecture.
Thank you.
Does anybody else have a question? can't see any raised hands, and since we're a little bit over time, what I'm going to suggest is that we invite people to unmute, and we give Matija a big round of applause to thank him for a lovely talk.